Hello, this is Frazier Nyasulu. I'm your instructor for 1510 Lab. Lab number 3, conductivity in aqueous solution. Let's talk a little about that. First, got this picture from your textbook, Silverberg, and I thought it was relevant. Conductivity. We think of conductivity in the sense of electricity. So this setup here, this is a powered line. Water, nothing. Sugar, no, salt is a solid phase, doesn't conduct. And here, a salt dissolved in water in aqueous solution, sodium chloride, it conducts. What does that say? It says ions are necessary, and that the ions have got to be mobile. Here's another figure from your textbook. Strong acid or strong electrolyte. The light is high, nice strong light output. Weak electrolyte, weak acid, dim. That's great. And so you can determine if these are the same concentrations, that you have more ions in one sim compared to the other. But we like numbers. It's okay to say Frazier is tall. I'm not. It's more reasonable to say Frazier is 5'9½". I actually don't know my height. Go figure. Anyway, so numbers are good. So we'll talk about how to measure conductivity. When I first thought about this lab, I decided, well, I've got these conductivity sensors. What am I going to do with them? It's like, I'm going to do something in 1510 Lab with them. It's like, ooh, okay, what? So I figured, hey, what factors affect concentration? I mean, conductivity. And I figured, surely concentration. Yeah, you'd have come up with the same thing had you been thinking about it. Concentration. So we want to be able to vary the concentration, measure the conductivity, and look at the results and make conclusions based on that. And then it's like, well, let's compare strong electrolyte, strong acid to a weak acid and see how they compare. So we're going to do that in lab. Then I figured, well, what's the other thing we could investigate? I figured, well, these ions are not all of the same size. Some are small, some are big and heavy. It's like, well, if they're the same size, do the heavy ones, as they are pulled along by this electric field, go slower? What is the effect of size or mass of the ions? And so I chose chloride, bromide, iodide. These are the halides. Gotta know the terminology. And then perchlorate. And so we're increasing size there. And we can look at the effect of size. The other thing I thought of is, what's the effect of charge? Hey, magnesium, 2+ moving, sodium +1 moving. Where is the grid current flowing? It's like, aha! So, you guys will compare sodium perchlorate, Na+, ClO4- and magnesium sulfate. Gotta know your ions, right? Mg2+, SO4 2-. That's cool. Then I figure, well, what else? It's like, okay, let's just measure stuff. Let's measure stuff. Well, what kind of stuff? Well, if we can, the stuff that we interact with in our usual world. Aha! So we go, well, let's measure Pepsi Cola or Coca-Cola. Oh, how about milk? Orange juice. Anyway, so there's some everyday products. You measure the conductivity, and based on the number that you get, you kind of reason, number one, who is in there that's leading to this particular conductivity. So a lot of inferred reasoning that you're going to do in this lab. All right, how do you do conductivity? Conductivity, you must apply voltage or power supply. I know that. And then I must measure current, non-voltage, non-current. If the current is small, then that thing is not very conductive. If the current is high, yeah. Another way to think of it is resistance. So anyway, let's see if I pick up some pointer options here, pen. And so conductivity is defined as current that's flowing in that system divided by the voltage. So if the current is low for a given voltage, then that thing doesn't conduct as well. But it turns out in order to do this, you have to have some plates, some metal plates. Here's the real thing. There's a platinum. It's called platinized platinum. That's why it looks black. And placed at distance. Two plates are placed at a known distance from each other in this solution, and you measure the conductivity. If this is plus, then the anions are coming this way. If this is minus, then cations are going that way. Right. So a current over voltage. That's cool. Makes sense. When the current is low for a non-voltage, then the conductivity is low. Well, it turns out that distance matters. The closer you place these plates here, then the higher the conductivity. So we must agree on the distance. So let's look at the sort of SI units: amps, voltage, and distance meters. Well, somebody who came before us, and they kind of thought about this seriously before, called this term current over voltage. Siemens are represented by S. So conductivity is Siemens per meter. Siemens per meter. So, yeah, there we go, Siemens per meter. And there it is, SI unit for conductivity. That happens to be a big unit. It's like counting my little income in billions. It's like, ooh. Well, anyway. So how about if we go, instead of Siemens per meter, micro Siemens per centimeter? And this happens to be, if you multiply this by 10 to the 4, you get the bigger guy. So, all right. So just a review here. Electrolytes, strong electrolytes, weak electrolytes, non-electrolytes. You've heard those terms in class. Let's take an ionic compound like sodium chloride. We visualize sodium ions and chloride ions. When we dissolve them, these go separate ways. They're independently mobile in solution, so they can go different directions under influence of an electric field. So, sodium chloride, put in 1 sodium, 1 chloride, you get 1 and 1. Put in 100, you get 100 and 100. Well, how about acetic acid? Acetic acid is molecular. It is molecular, and then it ionizes. And because it's a weak acid, it typically undergoes a small percentage ionization, let's say 10% or less. So if I take acetic acid, gotta know the formula for the acetate ion and the acetic acid, then it does this, but it goes to the right hand side only sort of 10% of the way. And so if we're looking at conductivity of the two of them, would expect conductivity of sodium chloride to be higher than conductivity of acetic acid. That makes sense? You're good. Moving right on, my friends. Procedure. Hey, it turns out that this is the probe here that we're going to use. The probe has a little hole there. Well, it turns out that the plates that we're going to use to measure are sort of, are sort of here, right? And so we're going to measure here. And so if we're moving between solutions, we better rinse. And then also, just to make sure that everything is homogeneous, that is, the solution is the same inside where we're measuring and outside, we not only have to mix the solution, gotta pull the probe up and down. So the conductivity sensor has 3 units: microsiemens per centimeter, 0 to 1,000, 0 to 10,000, 0 to 100,000. So you always begin here, and if it floods, then you go to next one, the next one. All right, so that's the setup here. The conductivity sensor hooked up to the data logger, and then with this setup here, conductivity sensor in the solution of interest. Effect of concentration. Hey, I could do this in about 5 minutes. Yeah. So 60 milliliters of water, and then we measure the conductivity of the distilled water. You should get a small number. That kind of indicates that the conductivity sensor is working fine. Sort of a 20 to 100 microsiemens per centimeter for our quality of distilled water. So that's what you get for the beaker. If you're getting something like 900 or something, talk to your TA. And first of all, rinse through that sensor with water through the hole to make sure it's clean. Let it sit a little, kind of wake up from its slumber, and then test it again. So, effect of concentration, 60 milliliters. Then you add 1 milliliter of 1 molar HCl with the autopipetter. You're now good at the autopipettas, right? Add the liter, then stir with the little stirrer. Then sensor up and down 3 times, put it in, make a reading. All right, the next one, do it until you've made 5 additions. Get another beaker, do the same with acetic acid, but this time do 7 additions. Done with the effect of concentration. About 8 minutes. Effect of charge. What are we looking there? Well, gotta see what's happening here. Yep. Sodium plus, sodium perchlorate. Gotta know your ions. Magnesium sulfate, +1 -1, +2 -2. And so we can, same concentrations, measure those and conclude, or based on your results, come up with the effect of concentration. Effect of size, as we talked about, all these are sodium-based ions, and so we go from chloride, bromide, iodide, and so on, and so we can then look at the effect of size or mass. And then we measure the conductivity of Windex, Pepsi, milk, orange juice, whatever. But we'll get those results, so it's not just measuring them. We'll look at that and then try and understand what is going on. Wear your goggles at all times. And in the case where you'll be handling dry ice, make sure you use tongs because the system is very cold. And for this lab, for sure, all solutions can go down in the drain. Just rinse with plenty of water. Short, mind-provoking. You guys will do most of the reasoning and not many calculations. Most of what you need to do in the lab, talk it out. You can learn a lot from interacting with others, discussing things, never copying. So it goes something like this. Hey, what's the effect of concentration? And Mr. J says, well, we're adding more, so the concentration is increasing and the conductivity is increasing. And so you discuss it and come to some agreement, but then everybody writes their own answer. If you end up with identical answers, one copied from the other, get a 0. That's not good. But we encourage discussion, checking with each other, because all of that is part of good learning. Have a great day, my friends.